So tonight we're going to have a couple of presenters, and I'm going to let Patrick Longmire go first. He's with the New Mexico Environment Department, and he is a water chemist. And he's going to tell you what being high on any of those levels means for you and to your health, the real basics of water chemistry. Then we've arranged for the Good Water Company, I think I see them in the hall, to talk to you about if you choose to treat your well water, what does that entail and how much does it cost, just for informational purposes. And that way, going into your well election, which should be fairly soon, within the next month or two, you'll be fully informed of what's going on.
Good afternoon, I'm Patrick Longmire, and I'm a native. My parents worked at Los Alamos, and we never really left. I've lived in France, but one thing I'm dedicated to in my life is water, because without water, we wouldn't be here. So I have been with the Groundwater Quality Bureau since February of this year. Prior to that, I retired from the laboratory in April of 2012 and took 9 months off to play music and go have fun, ride the bike, and went back to work with the state. And I was with the DOE Oversight Bureau in Los Alamos and conducting water chemistry research. So I've been involved with sampling around Nambe, Espanola, Tesuque, Santa Fe, and there is a lot of naturally occurring uranium in this area. And one of the sources of the uranium are from the granitic rocks that are in the Sangre de Cristos, and there's another source here that's in the valley fill, and we'll talk about that. So it's an honor to be here. If you have any questions, please raise them, and thank you for being here. So I hope everybody can see this. Can we go to the next slide? So what we're going to consider here is, first we'll talk about the results of the water fair. So in this July, we sampled about 195 waters. People brought their water samples in, sent them to Hull Analytical. That's an analytical laboratory in Albuquerque, and about the last 2 to 3 weeks had the results back, and letters went out to all of the well owners. Then I'm going to talk about, well, where did the natural uranium come from? And then we'll just have some summary and conclusions. Okay, next slide. So we sampled 195 waters, or we analyzed 195 waters, and 55% of those waters exceeded the EPA drinking water standard for uranium, which is 0.03 parts per million, or ppm. And the maximum uranium concentration we measured was 0.86 parts per million. So 55% is equivalent to 107 out of 195 water samples. This is nothing new. When I was at the lab, I worked with a great organization, the New Mexico Small Business, and worked with Good Water Company out of Santa Fe. We sampled about 600 wells, and I'll show some of those data here. So the results that we have here, that you folks have just received your results from, are very consistent from previous water fairs. Okay, so uranium, we know that there's natural uranium, and the 30 parts per billion, or 0.03 parts per million, is the chronic. If you live 70 years and you drink a liter of water a day, that's what that's based on, that number. So it's the chronic exposure of drinking water that has uranium.
Parts per million.
Parts per million.
Of what?
Parts per million of uranium in 1 liter of water.
But a million atoms?
No, not atoms, but if you had, say, a million years, which is a short period in geologic time, you take 30 of those years, that would be equivalent 30 parts per million, or 30 million years out of the total amount of year.
30 parts per million what?
30 parts per million of uranium in 1 liter of water, or another way to look at it is 30 parts per million in 1 million parts of water.
I think his question is like uranium oxide, or is it a compound, or is it?
Oh, it's just dissolved in the water.
So it's actually a uranium molecule.
It's a uranium molecule. And in the waters here, there is another mineral, bicarbonate. It's naturally occurring. Uranium, certain forms of uranium will chemically bind with that. So it's a dissolved molecule. Thank you, sir.
So there are 30 of those molecules,
30 parts.
per million molecules of other sorts.
You could consider it that way, yes. Okay, and now for arsenic, there's naturally occurring arsenic in the water. 18% of the water samples, that is 36 out of 195 water samples, exceeded the EPA drinking water standard for arsenic, which is 0.01 parts per million. And the maximum amount of arsenic that we measured was 0.029, so roughly 3 times the drinking water limit. And arsenic is, it's naturally occurring. It can be from, hot waters, what's called hydrothermal waters that are associated with volcanic rocks. And there is a fair amount of arsenic in Santa Fe, along Tano Road, west of Santa Fe, and that whole area here, La Cienega, Cerrillos, and generally the arsenic's associated with the volcanic rocks. Okay, the other constituent is nitrate. We only had 1 sample out of 195 that exceeded the EPA drinking water standard for nitrate, which is 10 parts per million nitrate. And so this 1 sample had 18 parts per million nitrate. Nitrate can be naturally occurring, but at lower concentrations. Most of the nitrate that we measure in the water here are from septic tanks.
I have a question, and I don't know if I hope it's relevant to other people too. When I have that sand filter.
Okay.
When I did the sample, I bypassed the sand filter to give you what exactly it comes out of the well. Now, if there's uranium, it's not really sand. I get like a stuff. It's finer than sand. Mm-hmm. Is it more likely to be in the water or in those particles?
It could be in both. Generally, the smaller the particle, the more that the uranium can attach on it. If you have water that has rust in it, iron oxide, uranium can be attached to that. The coarser, the larger the particle, the less attraction of the uranium to that particle.
What about magnesium?
Magnesium pretty much will stay in water. Magnesium likes...
No, but attaching, the uranium attaching.
To magnesium? In some cases, but not in the groundwater here. Magnesium, uranium is more associated with bicarbonate, which is, has an attraction for uranium. And when those two combine, you take that uranium molecule and bicarbonate, it can become very mobile in groundwater. And that's what we have here in the whole situation, going from the foothills east of Nambe, where the uranium is leaching out of the granites, and there's all this natural bicarbonate in the water. The uranium attaches to it, the dissolved uranium, and then it can move with the groundwater. Yes, sir.
Thank you. And so the liter, the chronic issue is the liter, which is basically a little more than a quart per day for 70 years. But my question is that 30 parts per million or billion, 30 parts per billion in the uranium, how many of those 107 wells were right at the 30 parts or just slightly?
That's a very good question. I don't have the exact statistics, but looking at the number, there were a handful that were right around 30, 32, 33, but then there were a whole bunch between 50 and going up to about 200. And this one value here of the 8.86, that was definitely the highest value. But most of them tend to cluster between 50 and 200 parts per billion, or 0.05 and 0.2. Yes, sir.
Is there any correlation between the higher concentrations of uranium and arsenic and the well depth?
That's a very good question too. So with this aquifer here, if you can imagine a huge sandbox that is about 8 to 10,000 feet deep, thick, and all that as these mountains were forming starting about 25 million years ago, all the sediment went into the basin that usually waters that are deeper down, say like 10,000 feet, will have more mineral content. Usually they can have higher arsenic or uranium. It all depends on the rock types where the uranium comes from.
And the water you collected,
So the water, so the water from the wells that we sampled, I bet most of those were less than 300 feet on that. Yes, miss?
We spoke on the phone a couple of days ago.
Oh, yeah, yeah. Nice meeting you.
I actually found my results from 2004,
Uh-huh.
and the uranium has gone down from 0.0548
To point, what was it, 0.026 or
0.028.
28? Yeah,
It's gone down by almost half
yeah.
in 13 years.
That's good.
Well, is that normal?
It can be normal, because as this, depending on how the water's moving, but that can be a normal situation. In other areas, depending, if you have a supply well or something and it's really pumping at a large rate and you're pulling in water from a greater depth, in some cases it may increase slightly. So it can vary over time, but in your case that's a good situation because now your value is below the EPA drinking water standard.
But is it gonna, or in your opinion, fluctuate every 10 years?
It could. I can't really say what it's going to do unless we sample it and see. No. But I'm glad that it decreased almost in half.
Almost half.
Yes, sir.
You know what the basis for setting the standards is? That is 30 parts per million. How is that number determined?
So I am not a toxicologist, but from what I've read, depending on tests in animals and the long-term exposure and doing calculations, that's what the numbers are based on. In honesty, I can't go into the details of that. Yes, sir.
One question, at what point does the uranium content of the water become dangerous to people?
Well,
What number?
so it would be the 30 parts per billion or 0.03 parts per million because that's what the drinking water standard is over the lifetime of an individual living to 70 years of age. But I have sampled lots of wells in this area, people that are in their 80s and 90s, and they've been drinking this water their entire life. And so what I'm saying is it is that's what they base the standards on, but there can be other factors as well too, lifestyles, etc. Yes, miss?
I have a follow-up to his question. So I live in Pojoaque, and I got the letter. And the part that really upset me was how can uranium affect my health? And it goes on to talk about how it's stored in the bones, liver, kidneys, how it can change the way your kidneys work and so forth. And being a healthcare provider now for 20 years, I thought, great, my patients are going to start to think that they have osteoporosis because of their well water. Or they have kidney disease, chronic kidney disease because of their well water. They're going to stop their meds, they're going to start asking questions, and they're going to be scared. So, I talked to the doctors I work with. I work with Dr. Mills, he's a nephrologist, a kidney specialist. And he looked at this, and if you want to turn the camera off, I'll tell you exactly what he said. Medication, or, oh, it's not my diabetes causing my kidney failure, it's the water. Wouldn't we like to believe that? It's not true. Keep taking your meds, and don't believe that it's going to have an impact on your health, because it is not.
Now, the uranium, that's in the water here. You could go within a square mile and sample the wells. It's not evenly distributed. There are areas that don't have uranium. And I'll show a map here where we do see, high uranium, because with the uranium being leached out of the granites in the Sangres is along the Pojoaque watershed, the Pojoaque River, and the groundwater that's underneath that, because that's been going on for hundreds of thousands of years.
Would you like the next slide?
Yes. Okay, thank you. Okay, fluoride. We had 4 samples out of 195 samples that exceeded the EPA drinking water standard of 2 parts per million, or ppm, fluoride. The maximum concentration we measured was 15 parts per million. Iron. So iron, there's a secondary standard for iron, and we had basically 9%, or 17 out of 195 water samples exceed the EPA drinking water standard for iron, which is 0.3 parts per million. There's just a lot of iron in the rocks. And usually, from a geochemical perspective, the more rust that you have in the rock, iron oxides, they have the ability to uptake these different metals. And iron is used as part of water treatment. And then the last one, manganese, we had 8%, 15 out of 195 samples exceeded the EPA drinking water standard for manganese, which is 0.05 parts per million. And the drinking water standard, is 0.005, and the highest we measured was 1.4 parts per million manganese. Okay, so the comment is that if you can collect the water from your wellhead that hasn't gone through water softeners or filters, if you measure, you'll get different chemical results from what was sampled directly from the well and then after the filters. That's why we wanted to know, what was in the water. But if you have a water softener, that removes calcium and magnesium, if you have a reverse osmosis, filter that removes metals like arsenic.
So if your well is over the limit, there are possible treatments.
Absolutely, there are. So we've lived in Santa Fe since 1980, we're over in Casa Solana. And we were off of the Buckman well field, and that water is really mineralized. We've dated that water with carbon-14. It's older than 25,000 years old. Before I got a reverse osmosis filter, the uranium concentrations were 29 parts per billion, or 0.029 parts per million. So I was 1 part per billion below the standard. And we bought an RO unit, and the uranium now is below 1 part per billion. So there are options. There are options that will work.
Does uranium accumulate the same way that arsenic does? Or
Generally, uranium and arsenic will affect kidneys and liver. But they occur as different molecules, and there's 2 forms of arsenic, and one is called arsenate, where it's the oxidized form. One is arsenite, the reduced form. It's actually the arsenite that is the more toxic form. And the New Mexico Environment Department is proposing right now our groundwater standard, not the drinking water standard, but the groundwater standard is 0.1 parts per million, or 100 parts per billion. That's being proposed to be equivalent to the EPA drinking water standard of 10 parts per billion. And there is, in the Southwest, there's a lot of natural arsenic that's associated with volcanic rocks. In India, in Bangladesh, they have granites, and there's a mineral called pyrite, or fool's gold, iron oxide. And and naturally in that mineral, there's a lot of arsenic concentrated. When that mineral breaks down, there's a lot of arsenic. People in Bangladesh use water treatment like iron filters to remove the arsenic. Yes, sir.
Is lead not a problem here?
Lead usually isn't a problem. It's associated with soldering and, you know, and in pipes, and I'm sure we're all familiar with Flint, Michigan. But, you know, natural lead in groundwater is very immobile. It likes to react with the mineral surfaces, so it doesn't move like uranium does. Yes, sir.
Can you give a description of practical quantitative limit?
Okay, so when we collect the samples, we send them to the analytical lab. The lab is using these different instruments to measure the concentrations, and the practical quantitation limit is the limit where there is 100% certainty of that value. So like if you look at your data sheet, what, sir, for arsenic, what do they list as the practical quantitation limit, PQL?
0.005.
Okay, 0.005 parts per million. At that level or higher for arsenic in that sample, there would be 100% certainty on that concentration. Below that is another value called the detection limit, where the instrument sees a little bit, but there's more uncertainty on how precise is that number. So if you have, you know, values that are above the practical quantitation limit, there's a very, very good precision and accuracy on those numbers. If they're less than the practical quantitation limit, but above the detection limit, which is the lowest value, you know, the instrument sees it, but there can be more error, you know, or more uncertainty. And if it's below the detection limit, the instrument just can't measure it. Yes, sir.
You keep saying the drinking water. I think most of, at least my exposure would be through bathing and washing food.
Yeah.
Cooking with
Dermal
food.
contact.
Yeah. Is that, would that be considered drinking water contact as well?
Not really, because, you know, you're not drinking a liter of it. If you're taking a shower, you know, and you wipe yourself off, there's less chance of actual, you know, uptake of that water into your body. Okay, so here just this bold outline shows what is described as the Espanola Basin, and it's just a geologic province. So the other part here, it's north of 285 around Tres Piedras and goes all the way down to La Cienega. And what I wanted to show here is with uranium, this area shows the Sangre de Cristos, and that is the Sangre de Cristos when they started to lift up, you know, like 25 million years ago, and water was reacting, you know, all the snow melt over all those millions of years. It leached the uranium out of the granites, and that's where the, you know, one source of the uranium is. There's another source here. We can look out this window, and the kind of the brownish colored sediment, that's called the Tesuque Formation, and I'll show a slide, but in that Tesuque Formation there's volcanic ash that is much older than the Jemez Mountains. It's about 25 million years old. The ash that came from the Jemez Mountains is more like 1.1 or 1.5 million years old. That can be another source of uranium. So this is the Espanola Basin, has different geology, and basically where the uranium occurs around Nambe, Espanola, Tesuque, Santa Fe, it's within from the Sangre de Cristos and from these sediments that fill the valley. Okay, next slide. So this, you really can't see this, but the arrows here show the direction of groundwater flow. So you know, and this gets into our water supply. You know, the Sangre de Cristos, so some of those peaks are what, you know, 12,000 feet, you know, the Truchas peaks. Over hundreds of thousands of years of every year having a winter and snow melt. That's that snow melt that slowly infiltrates through the rocks, help fill up this big sandbox, this aquifer we have. We get, you know, torrential monsoonal rains. That can help fill up the upper part of the aquifer. But we have water that is originated in the Sangre de Cristos, and like if we look at the age of the water that's in the Buckman well field, that's over 25,000 years. It took 25,000 years from that water to move from the mountains through the aquifer to where the Buckman well field is. So, so the water, as it's migrating through the rocks, it's reacting with the rocks. So you have the best or the least mineralized water generally up in the mountains near, you know, where the snow melt is, and you can have the more mineralized waters as the water gets older and is migrating farther along the flow paths. Okay, next slide. So this is just an article from Saturday, July 30th, the Sunday New Mexican in Santa Cruz, where they're trying to work on their water supply. Santa Cruz has a lot of natural uranium in the water. So this issue is, you know, it's very important to all of us, and I just wanted to show this. Okay, we really can't see this picture, but how many of us have noticed by, you know, say driving up to Chimayo, where you see these kind of white layers in the sediments? That's the ash, and that's the source of the uranium in the Tesuque Formation. Okay, next slide. So this basically shows we have two sources of uranium. One is up in the Sangre de Cristos, the granites, okay? And for, you know, 25 million years or so, that, you know, those granites, they've uplifted and they're reacting with rock, with water and wind, and they break down, the minerals get exposed, and uranium leaches out. And then the other source is that volcanic ash I talked about in the Tesuque Formation. This map here, and I'm sorry it's not very clear, but these red circles indicate wells that we sampled back in 2006, 2007, 2009, where the uranium is at or above the drinking water standard of the 0.03 parts per million or 30 parts per billion. And where you see this is right along the Pojoaque River and this whole area. So the uranium is derived both from the Sangre de Cristos and then from the volcanic ash.
You also have it in Santa Fe as well as other places.
Yeah, like down here in Santa Fe. The yellow indicates it's between 15 and 30 parts per billion.
Given what Sarah said earlier about how her uranium has been cut in half now,
Yes.
I think it'd be very telling to have a comparison of a 2006 slide and a 2017 slide of your two.
Absolutely, and I thought of that too. So as we have the data in, is that's one of the things I want to do, to compare, see where it's increasing. Is it the same or is it decreasing? Yes, sir.
Since you worked at Los Alamos, could you say something about the findings? I know the lab was testing water going down from Los Alamos to see what was there. Can you say anything about what they found and like how far afield they found things?
So for probably 4 decades or more, Los Alamos has been sampling the waters and the surface water. Los Alamos, the uranium that's in the water supply wells at Los Alamos is between about 0.5 and 1 part per billion. It's very low uranium. But the aquifer, those rocks are a lot younger than what's here on this part of the basin. I have been recently involved in looking at pharmaceuticals in water. And so this is everywhere in the country. You know, you have a wastewater treatment plant. I'm just as guilty. I have to take a generic statin drug. You think from all the exercise I get, I wouldn't have to worry about cholesterol, but I do.
And you eat all that vegetable?
And I eat all that
Oh, man.
You chose the wrong
vegetable. Well, no, my parents were great parents. But what I'm saying is that we need to be aware of a lot of other sources. And pharmaceuticals, you know, then wastewater treatment plants, you've got to look at where's that water going and who's, you know, what's being discharged into the Rio Grande, et cetera. Now, there are no drinking water standards for pharmaceuticals, but who knows, maybe 30 years from now there may be. Okay, next slide. Okay, so You'll have to look at the PDF, but the uranium is associated with rust in rocks. You see, the outcrops here between Nambe and Chimio, and if you see, brown colors, we've gone out and sampled those buttes with the iron. There's uranium associated with that. So iron and uranium geochemically have an association, okay? And this just shows where we've sampled from the other water fairs around Santa Fe, and these little bar plots here show where we had arsenic, fluoride, nitrate, uranium, and so there's a lot of mineralized waters around Santa Fe. And so the blue here is arsenic, the magenta's fluoride, nitrate is green, and uranium's yellow. So this whole area, is just, it's mineralized with, arsenic or uranium or fluoride. Yes, sir.
There's a study published in 2010, I think it was. You were probably one of the authors. Or actually, no, it wasn't published, but the maps were put up at the Ivy Center for 2010. It showed high levels of manganese and Kuyamake.
Okay.
Did you find this time around?
There was some manganese, but not a lot, and you need special conditions to get manganese to dissolve into water.
Next slide.
Yep, next. Okay, so summary conclusions. These are excellent questions. I know I've run over, but I really appreciate everybody's input. We sampled 195 water samples at the Pojoaque Water Fair in July 2017. The results show that uranium, arsenic, fluoride, iron, manganese, and nitrate exceeded the EPA drinking water standards as part of the fair. And then with uranium, it was about 107 samples out of 195. Arsenic was 36 samples. 36. Fluoride 4, nitrate 1, iron 17, manganese 15. The uranium, arsenic, fluoride, iron, manganese are all naturally occurring. Nitrates associated with septic tanks. We've known for a long time that uranium has been above the drinking water standard. We sampled one well, and the gentleman was about 70 years old, probably still living. He was drinking 1,800 parts per billion uranium without a filter. So, and then the source of the uranium is from the Sangre de Cristo Mountains over millions of years of just leaching the uranium out of the rocks. And then some of the ash that's within the basin is a source of the uranium.
Okay, so my question is, with all of the results, did I hear you say that a reverse osmosis would take care of this if we invested in that opposed to?
It does for our drinking water in our home. And we just have it for drinking water. We use the other water for bathing.
So given all of the numbers that we have been over and reviewed, you're saying that a reverse osmosis would be a way to take care of our water?
For arsenic and iron and uranium, especially uranium. Yes, indeed.